Okay, so today we'll go over a few of the things which regard to analysis of the log file and how to calculate the RMSD, how to align a protein, how to calculate the secondary structure from the timeline, and how to calculate hydrogen bonds. These things were discussed yesterday in class. So today I'm just uploading the same. How to do it. So the first thing is to understand your log file. So for example, I have a log file here, which is npt.log. This is the same log file which you saw. So if you scroll down, you see this, right? These are the various columns you will see. This is the timeline, time step number, that is here. This is the bond energy, angle energy, dihedral, improper, electrostatic, van der Waals, these are not required, kinetic energy, total energy, temperature, potential. So all these things are there, right? Pressure, group pressure, average, etc. So the log file contains for every time step all this information. So we can actually plot this in VMD. So open VMD either by if it's a Windows, you go to VMD and double click. If it's a Linux, Ubuntu, you just can type VMD in the terminal. So go to extensions, analysis, you say NAMD plot. So this window will open. In the NAMD plot, you need to first upload the file. Select NAMD data. So here I have this NAMD plot open. So this file has been uploaded. Now we can select what we want to plot. For example, I want to plot temperature. You can say file, plot selected data. You will see temperature. So I assume this simulation was done at around 310 Kelvin. So you see the mean is around 310 Kelvin. This just tells you that the thermostat is working on, right? So we can calculate many other things. So let's say if I want to calculate the electrostatic energy, you say plot selected data, you get the electrostatic energy. I can calculate the bond or angle, dihedral, or even electrostatics, van der Waals, right? All these are kinetic. If I say plot selected data, all these energies are there. Of course, since my I think this is the electrostatic energy is very negative. So to accommodate everything in this thing, it looks sort of this. So right, but so if you want to plot individually, you will see better, right? So for example, if I just remove electrostatic from here, and if I just say plot selected data, so you'll get this. Okay? And this, if you want, you can copy into your file, right? Export to PostScript, you can export to XML to plot, etc. Print. So, right, everything you can export it. All this data you can obtain. Okay, this is what, and you can also just check since it's NPT. You can check the volume. So the system here, the log file doesn't have any information on the system you have. So here it's a ubiquitin protein in water. But anyway, so you can plot volume. Check what is it. Uh, yeah. So I think there is some. Okay, so since I have dihedral, it's calling, so you should uncheck this. So now it will only plot volume, plot selected data. As you see, its volume is also sort of stabilized. Okay. So now let us, once we have this, now let us load the PSF and PGP which we had. So let's say new molecule. First you load the PSF. Okay, load. Again, you need to go to browse. Again, you should not go to file new molecule. So browse, now upload the DCD. Okay, load. Right, so there are 300 frames, so it takes some time for it to load. Okay, so 300 frames, this is the box. You can get the extensions, TK console. I'm not going to go deep here, so you can get what is the PVC get. This is the box size. And you can create just a representation for protein. So you say graphics, create new representation just so that you have protein. You can see the protein. Here you uncheck this. So now you have just the protein. Now it is always better to, while you are coding the secondary structure, it will take whichever structure you are as the reference structure. So it's better to bring it back to frame 0. So this is my reference structure, right? So frame 0. Now you make it, let's say, new cartoon, the secondary structure. So you see it contains this yellow ones. In the new cartoon, this representation actually you're only traversing along the backbone of the protein. Okay, you have not there's no side chains, etc. Because this is the representation. So all these yellow ones are the beta sheets. The pink one is the alpha helix. These ones, the one in blue are G10 helix, but these are not as stable as alpha helix. These are just small residues. So they keep transforming between turns and G10 helices. So the white ones are the coils and the green ones are the turns. So there's not much of a difference actually, if you speak. But anyway, so what are the things I can do? First is if I play this, you see the protein is moving around, right? So actually here it is not that much, but if I had run, this is only for 3 nanoseconds, I think, or 6 nanoseconds, I don't remember, 6 nanoseconds. But if I had run longer, it sort of moves around the box. So the first thing to do is to align the protein. So you go to extensions, analysis, RMSD trajectory tool. When you say here, when you say you have chosen protein, and here you click only the backbone, selection modifiers backbone, and you're saying on off reference frame 0, so align. So it will align keeping reference as the screen as frame 0 as the reference. Okay, align. Okay, so now it's aligned or not. You can check if you play this movie. You'll see it sort of superimposed whatever fluctuation is occurring on top of the reference frame. So now you can clearly see that if you rotate this, you'll see that the protein as such, there is no change at all. So it's sort of stable, there's no structural changes occurring, and it's not just moving around everywhere in center. Once this is done, you can calculate the RMSD, and I'm not going to save. If you want to save, you can even save. I'm just going to say plot, and yes, I'll just stop. I'll say plot RMSD. Remember the reference frame is your first frame. So you say RMSD, and you see RMSD is the variation is very less. Okay, we'll see for some cases where the variation is very high. Here the variation is very less. Okay, this is how you calculate RMSD. The other thing is to calculate hydrogen bonds. The same thing, extensions, analysis, hydrogen bonds. So this is the PSF already there. So protein, between protein means you can only specify one. But if it's between protein water, you need to also specify water here. If it's water, you can just specify water. But if it is water and protein, it should be protein, and here it should be water. I'm just first looking at protein. This distance, as we discussed, you can reach this to 3.2. This is 20, and everything else is fine. You say find hydrogen bonds. It plots these hydrogen bonds. If you want, actually, you can write this into a file. Okay. So this is the protein hydrogen bonds averaging around 25. Now, as we discussed in class, if I increase it to 3.4 or 3.6, so this now it should increase, right? So, right, all of you are seeing. And if I just do this for water, waters, it'll take some time because there's a lot of water molecules. You have this particular, so you have almost 2720. So with this, I'll end today's session. Thank you. Stop.